So guys, welcome to our channel once again. In today's video, we have here these 10 questions to answer on the topic electric field. So this video will be about capacitance, arrangements and application. So in short, to stay till the end of this video. Let's go ahead and consider the first question here. It says, a capacitor of capacitance 25 microfarads is connected to an AC power source of frequency 200 over pi hertz. Calculate the reactance of the capacitor. So guys, in order to calculate for the reactance here, we have reactance, which is XC here, is equal to 1 over 2 pi FC. So take note of this formula. Reactance, which is XC, is equal to 1 over 2 pi FC. So in order to impute these parameters from this equation, we're going to have 1 over 2 times pi times the frequency, which is 200 over pi, then times the capacitance, which is 25 microfarads. That's 25 times 10 to the power of negative 6. Now, in order to resolve this, we are going to bring up this pi from these 200 over pi. So when you have a number divided by a fraction, you can always bring up the denominator of the fraction. So the denominator of this fraction will have to go up, and that's pi goes up here. And then again, since this is 10 times a negative 6, we can bring it up here and call it 10 times 6, which is now a positive 6. So let's now impute the rest of the denominators here. This is 2 times pi times 200 times 25. So now that we have this in this format, the next thing we are going to do is to cancel out pi. So when we cancel out pi, we can now go ahead and have that 10 to the power of 6 over, so 2 times 200 is 400, then 400 times 25 is 10 to the power of 4. So that's actually a 10,000 though. So 10 to the power of 4, 10 to the power of 6 over 10 to the power of 4 will give us 10 to the power of 2. That's 100, guys, and that's option A. So option A is the answer to this question. Let's go ahead and consider the next question. So that's question number 2 here. It says the energy stored in a capacitor of capacitance 5 microfarads is 40 joules. Calculate the voltage applied across its terminal. So guys, let's recall the equation E is equal to half QV, and let's also note that Q is equal to CV. So in that case, E is going to be 1/2 of CV squared, since Q is actually CV. So CV times V is CV squared. So in this case, V squared, if we make V squared the subject of this equation, it's going to be V squared is equal to 2 times E over C. So this will be 2 times 40 over 5 times 10 to the power of negative 6. So recall that we have here 5 microfarads, and micro is 10 to the power of negative 6. So with this, we can bring up the negative 6, as always. So if we bring up this negative 6 to the numerator, it changes to a positive 6. So we have 2 times 40 times 10 to the power of a positive 6 here, and this will be over 5, which is the capacitance. Now, so if we solve for this, we are going to have 16 times 10 to the power of 6, and then it means that V squared is equal to 16 times 10 to the power of 6. Now, V alone is going to be the square root of this. So the square root of 16 times 10 to the power of 6. And that's going to give us, so option C is the answer to this question. Let's go ahead and consider the next question, guys. So that's question number 3 here. It says 3 capacitors, each of capacitance 1.5 microfarads, are connected in series. The total capacitance in the circuit is, alright, so for this we are going to use this formula. So when capacitors are connected in series, we have 1 over the total capacitance, let's say CT, is equal to 1 over the first capacitance, let's say C1, plus 1 over the second capacitance, let's say C2, plus 1 over the third capacitance, let's say C3, and so on. So in this case, 1 over the total capacitance will give us 1 over 1.5 plus 1 over 1.5 plus 1 over 1.5. So let's take note that each of the capacitors will have a capacitance of 1.5. So that's why we have each of these as 1 over 1.5, 1 over 1.5. Now, this way, the next thing we are going to do is to actually resolve this. So we are going to do it this way. 1 over CT as 1 of the over the total capacitance will be equal to, so let's find the LCM of these three, and that's 1.5. So 1.5 over 1.5 is actually 1, and that's 1 times 1 here is 1. So this will be plus. So we'll do the same thing here to get 1 and multiply by 1. That's another 1. Then plus, we'll do the same thing here and still get 1. So this will be 3 over 1.5. So let's go ahead and write it here, 3 over 1.5. So 1 over CT here, 1 over CT is equal to 3 over 1.5. So this way we can simplify this further, since we can say 3CT. So when we multiply this, we have 3CT is equal to 1 times 1.5 is still 1.5 here. So it means that CT alone will be 1.5 over 3, and this will be equal to 0.5 microfarads. And that's it for this question, guys. So let's go ahead and consider the next question. That's question number 4 here. It says the equivalent capacitance of a 3 microfarad capacitor and a 6 microfarad capacitor connected in parallel is, okay, so guys, this is what we'll do here. These capacitors are connected in parallel, so which means the total capacitance CT will be equal to C1 plus C2 plus C3 and so on. So since we have C1 plus C2, we just have 2 capacitors here. So let's use C1 and C2. So CT will be 3 microfarads plus 6 microfarads, and that's going to be 3 plus 6, that's 9 microfarads. And that's it for this question. Option B is the answer to this question. Let's go ahead and consider the next question, guys. That's question number 5 here. It says the quantity of electric charge stored in a capacitor is measured in A, volts, B, farad, C, ampere, D, coulomb. So guys, the answer to this question is option D here, and that's coulomb. So let's go ahead and consider the next question. So that's question number 6 here. It says 2 capacitors, each of the capacitance 2 microfarads, are connected in parallel. If the potential difference across them is 120 volts, calculate the charge on each capacitor. So guys, for this, let's go ahead and solve this together. Now, it says here there are two capacitors connected in parallel. So obviously the equivalent capacitance of this will be CT is equal to 2 microfarads plus the other 2 microfarads, and that's 4 microfarads here. So we'll have 4 microfarads as the total capacitance of these capacitors connected in parallel. And then it says here we should calculate the charge on each capacitor. So now let's also employ our formula that Q is equal to CV. So if Q is equal to CV, so let's also note that for a parallel connection, the voltage across the system is the same. So the V1 is equal to the V2. So the voltage remains the same. So in that case, since V1 is equal to V2, let's solve to know what each of the charges will be. So the charge will actually be the sum of charges, while the voltage will be the same across the system. So with this known, we're going to have that Q, or Q total, that will be the capacitance, which is 4 microfarads, times the potential difference, which is 120 volts. So the total charge will be 480 microcoulomb. So 480 microcoulomb is going to be the total charge. But then remember that the charge here will be, the total charge here will be the sum of charges. So the charge on its capacitor will now be 480 microcoulombs over 2, since the total charge is like 2 times the each charge. So 2 times each charge is 480 microcoulomb. Then each of the charge here is now going to be 480 microcoulomb over 2, which is 240 microcoulomb. So 240 microcoulomb is the same as 240 times 10 to the power of negative 6 coulomb. And if we want to resolve this in standard form, this will be 2.4 times 10 to the power of negative 4 coulomb. And that's it for this question. Option D is the answer to this question. So let's go ahead and consider the next question, guys. So that's question number 7 here. It says, a parallel plate capacitor of capacitance 600 microfarads has a potential difference of 2000 volts between its plates. Calculate the charge on either plate of the capacitor. So that's question number 7 here. It says, a parallel plate capacitor of capacitance 600 microfarads has a potential difference of 2000 volts between its plates. Calculate the charge in either plate of the capacitor. So guys, in order for us to solve this question, we are still going to employ the formula Q is equal to CV. Then we know that for parallel connection, V here should be the same across the system, while Q should be the sum of charges in the system. So here, having known this, we have two capacitors, 600 microfarads each. So 600 plus 600 will be 1200. So 1200 microfarads times 2000 volts. So this will give us, let's go ahead and check it out on the calculator. So 1200 times 2000, so that's 2.4 million. So it means that the total charge here will be 2.4 times 10 to the power of 6. So that's the total charge here. But then the question says calculate the charge on either plate of the capacitor. That's for 1. So we know that on either plate of the capacitor, this will be 2Q is equal to 2.4 times 10 to the power of 6. Then Q alone will be this over 2. That's 2.4 times 10 to the power of 6. So let's recall that this is actually micro charge. So that's microcoulomb. So this will be over 2, and then if you divide this by 2, you have 1.2 times 10 to the power of 6 microcoulomb. So in order to get the charge in coulomb, you just simply multiply this by 10 to the power of negative 6, or you simply divide it by 10 to the power of 6. So you have 1.2 coulombs. And that's it for this question. So the answer to this question here is option B, 1.2 coulombs. So that's it. Let's go ahead and consider the next question, guys. So that's question number 8 here. It says, two capacitors of capacitance is 0.4 microfarads and 0.5 microfarads are connected in parallel and charged to a potential difference of 50 volts. Determine the total charge acquired. So guys, this is going to be very simple. Since we are just going to determine the total charge, Q is equal to CV, and then C here for a parallel connection is going to be 0.4 microfarads plus 0.5 microfarads, and then all these together will be multiplied by V, which is 50 volts. So 0.4 plus 0.5 is actually 0.9 microfarads here. So when we multiply this by 50 volts, we're going to get 45 microcoulomb. So guys, our Q here is going to be 45 microcoulomb. So if we want to have this in coulomb, we can multiply by 10 to the power of negative 6, and we'll just get 4.5 times 10 to the power of a negative 5 coulombs, and that will be the answer to this question. But looking at the options here, we already have the options in microcoulombs, and here option B is the answer to this question. That's 45 microcoulombs. So that's it for this question, guys. Let's go ahead and consider the next question. So that's question number 9 here. It says the capacitance of parallel plate capacitors A varies inversely as the distance between the plates. B varies directly as the square of the distance between the plates. C varies directly as the distance between the plates. D varies as the square of the distance between the plates. So guys, the capacitance of parallel plate capacitor varies inversely as the distance between the plates, and that's option A here. So that's the answer to this question. Let's go ahead and consider the next question and the last. That's question number 10 here. It says when two flat plate conductors are arranged in such a way that they pass equal and opposite charges separated by a dielectric, they form A/an A capacitor, B electroscope, C electrophorus, D cell. So guys, the answer to this question is option A, and that's capacitor. So that's it for this question, and this is where we'll end this video for today. If you enjoyed this lesson, please give it a thumbs up. Don't forget to subscribe to this channel if you're not yet a subscriber. Also, if you have any specific question regarding this video, you can drop your question on the comment section below, and we'll ensure to give you a response. So finally guys, we want to encourage you to join our YouTube channel community. Thank you once again for watching this video and see you on the next one.